Good evening, sir. My name is Dhanambalan Adishivam. My matrix card number is 14-20F1052. Now I am going to present about gate turn-off Tyristor. Introduction. Although the Tyristor is extensively used in high-power applications, it always suffers from being a semi-controlled device. Even though it could be switched on by applying a gate signal, it has to be turned off by interrupting the main current using a commutation circuit. In case of DC to DC and DC to AC conversion circuits, this becomes a serious deficiency with Tyristor due to the absence of natural current zero, as in case of AC circuits. Hence, the development of gate turn of Tyristor addresses the major problems of the Tyristor by ensuring the turn-off mechanism through the gate terminal. GTO symbol. As GTO is a 3-lead Tyristor, it contains anode lead, cathode lead, and gate lead. The symbol of gate turn-off Tyristor is very much similar to SCR Tyristor, except for the gate terminal. Gate turn-off Tyristor is capable of both turning on and turning off the device. As this function is exhibited at the gate terminal, the gate terminal is represented with a two-way arrow connection that symbolizes this feature of Tyristor. The figure below shows the symbol of gate turn-off Tyristor. Structure of gate turn-off Tyristor. Gate turn-off Tyristor has a 4-layered PNP structure. The regions are represented as P plus, N minus, P, N plus. The anode of the device is connected with a heavily doped P plus layer. The cathode of the device is connected to a heavily doped N plus layer. Gate is also connected to another heavily doped P plus region. The structure of GTO is shown below. Basics of gate turn-off Tyristor. Gate turn-off Tyristor for GTO is a 3-terminal bipolar semiconductor switching device. Similar to conventional Tyristor, the terminals are anode, cathode, and gate. As the name indicates, it has gate turn-off capability. These are capable not only to turn on the main current with a gate drive circuit, but also to turn it off. A small positive gate current triggers the GTO into conduction mode, and also by a negative pulse on the gate, it is capable of being turned off. The gate has double arrows on it which distinguish the GTO from normal Tyristor. This indicates the bidirectional current flow through the gate terminal. The gate current required to turn off the GTO is relatively high. For example, a GTO rated with 4000 volt and 3000 ampere may need negative 750 ampere gate current to switch it off. So the typical turn-off gain of GTO is low, and it is in the range of 4 to 5. Due to this large negative current, GTO are used in low power applications. Principle of operation. The turn-on operation of GTO is similar to conventional Tyristor. When the anode terminal is made positive with respect to cathode by applying a positive gate current, the whole current injection from the gate forward bias the cathode P base junction. This results in the emission of electrons from the cathode towards the anode terminal. This induces the whole injection from the anode terminal into the base region. This injection of holes and electrons continues till the GTO comes into the conduction state. In case of Tyristor, the conduction starts initially by turning on the area of cathode adjacent to the gate terminal, and thus by plasma spreading the remaining area comes into the conduction. Unlike a Tyristor, GTO consists of narrow cathode elements which are heavily interdigitated associated with gate terminal. Thereby, the initial turned on area is very large and plasma spreading small. Hence, the GTO comes into the conduction state very quickly. To turn off a conducting GTO, a reverse bias is applied at the gate by making the gate negative with respect to cathode. A part of the holes from the P-base layer is extracted through the gate, which suppresses the injection of electrons from the cathode. In response to this, more hole current is extracted through the gate. It results more suppression of electrons from the cathode. Eventually, the voltage drop across the P-base junction causes to reverse bias the cathode injection, and hence the GTO is turned off. By the application of high negative gate voltage, these filaments are extinguished rapidly. Due to the N-base region stored charge, the anode to gate current continues to flow even though the cathode current is decreased. This is called a tail current, which decays exponentially as the excess charge or carriers are reduced by the recombination process. Once the tail current reduces to the leakage current level, the device retains its forward blocking characteristic. Gate turn-off Tyristor application. Due to advantage like excellent switching characteristics, no need of commutation circuit, maintenance-free operation, etc. makes the GTO usage predominant over Tyristor in many applications. It is used as a main control device in choppers and inverters. Some of these applications are AC drivers, DC drivers or DC choppers, AC stabilizing power supplies, DC circuit breakers, induction heating, and other low power applications. Characteristic. Reverse bias characteristic. In the reverse bias condition, the cathode is positive with respect to the anode. At this point, the N plus layer, P plus layer will be reverse bias as well as N layer, P plus layer junction. Thus, these two reverse bias junctions will not allow the flow of current from cathode to anode. Consequently, a very minor current flow in the device and in a reverse bias condition. When a breakdown occurs in this region, a larger current flow occurs. Forward bias characteristic. In the forward bias condition, the anode is positive with respect to the cathode. Now both N plus P junction and N minus P plus junction both are in forward bias condition. Here the central function P negative N gets reverse bias. Due to this, only a minor amount of current flows before the breakdown of the junction. At this point, if a positive pulse is applied, a breakdown occurs and the device gets turned on. After breakdown, larger amount of current flows into the circuit.